Prof David Pollard is now from Stanford and our Wollaston medalist is going to tell us about a new curriculum for a first course in structural geology. And as I read your title, David, I was looking at my bookshelf, not the one in the picture here, but my real, much smaller one at home. And I've been pretty good at recycling textbooks, and I looked for my structural geology textbooks, and the only one that's actually survived many moves and is still there is John Ramsey's Folding and Fracturing of Rocks. It's a bit gnarly as well, so I'm looking forward to this new curriculum you're offering us to understand and take forward structural geology. David Pollard, over to you.
Thank you very much, Mike. Let's see if we can get the various parts here working. I'm going to share my slides. Share that screen.
Looking good.
Okay, I presume you can hear me and you can see the first slide.
We can hear you, or at least I can hear you, and I can see the first slide. Yes, thank you.
Great. Okay, so today I hope to convince you it's time for a new curriculum for the first course in structural geology. You might ask, what's the rationale for a new curriculum? Mike mentioned that textbook that many of us are familiar with. And I do have to mention, I spent a year at Imperial College doing the MSc course with John, so that book is very familiar to me. On the other hand, if you look at the spectrum of textbooks, they provide an encyclopedic coverage of structures, but at best a sort of ad hoc and incomplete approach to the physical processes forming those structures. There are some exceptions, and John's book is an example. Typically, the undergraduate book doesn't employ the prerequisite math. There's relatively little calculus. And the prerequisite physics, Newton's mechanics, turns out to be incapable of explaining even the simplest geologic structures. So let's step back. This is where Newton's mechanics first came to light. His second law, F equals ma, force is mass times acceleration, from the Principia, is of course a cornerstone of all first courses in university physics. As conceived, it applies to objects like the little point masses that one sees. I'll get my pointer here, if I can. These little point masses, and perhaps to some degree of approximation, the planets themselves, which is what Newton was after. The timeline on the next slide will show that the Principia preceded the founding of geology by at least a century. And one might well ask, what, if any, role did F equals ma play in the founding of geology? So there's the timeline, stretching from 1650 to 1850. Newton's Principia is here, 1687. Hutton, Playfair, Lyell, names you're all familiar with, and others, of course, laid the foundation of geology from 1750 to about 1850. They must have known Newton's F equals ma, but did they use it? We will examine that question in the context of Hutton's influential trip to Siccar Point, Scotland in 1788, almost exactly 100 years after the Principia. So here we are at Siccar Point, a place many of you probably have visited. The Silurian greywackies are rotated to nearly vertical, and the younger Devonian red sandstone lies on this eroded surface, which is known now as Hutton's unconformity. Hutton used the observed geometric relations to assign relative ages to the greywackies, older, the sandstone, younger, and to identify the now famous unconformity as a gap in time when events must have transpired that are not recorded in the rock record. He used his principle of uniformitarianism to interpret the physical processes operating in the past based on those he could see operating in the present. Clearly, the deposition, the tilting, the erosion of the greywackies, and the subsequent deposition of the sandstone must have taken an immense span of time. This led, of course, to his conjecture that several thousand years for the entire age of Earth, the church dogma at his time, was completely untenable. So Hutton's insights broke the veil of church dogma like the waves crashing on this point in Scotland. However, the vast collection of rock particles at Siccar Point, each acted on by its neighbors, for those it was not obvious how to apply Newton's law to quantify, in Playfair's words, the immeasurable force which has burst asunder the solid pavement of the globe. Hutton was left with qualitative conjectures and analogies to observed active processes. Today, students of structural geology still face Hutton's dilemma. Newton's mechanics, F equals ma, from their prerequisite physics course is inadequate to calculate the causative forces or resulting velocities. To solve Hutton's dilemma, let's look again at that timeline. So here we are, the century from about 1750 to 1850 that saw the founding of geology, also witnessed the founding of continuum mechanics by Euler, Lagrange, Cauchy, and others. To understand how continuum mechanics resolves Hutton's dilemma, we review their contributions and put them in a geological context. This spectacular NASA image of the Zagros Mountains of Iran shows these black, roughly 5-kilometer long glaciers of salt oozing out of the anticlinal mountain ranges and flowing across the adjacent valleys. Euler, whose mathematical machinery we now call the spatial description of motion, enables one to quantify, for example, the vector field of velocity of the salt at every position x and time t. This photograph was taken on one of the basaltic dikes that radiates from this spectacular volcanic edifice known as Shiprock in New Mexico. Using Lagrange's mathematical machinery, now called the referential description of motion, one can, for example, calculate the vector field of displacement as a function of, again, position and time, as the pressure of the molten basalt pushed the Manco shale apart to open this dike. What Cauchy did was to use these descriptions of motion from Euler and Lagrange and applied conservation of mass and momentum to quantify the deformation of a material continuum and provide the foundational laws for what we now call continuum mechanics. While Newton's mechanics for isolated point masses can't help us understand, for example, these ornate folds at Millick Haven, Cornwall, his continuum mechanics can. The new curriculum uses continuum mechanics to resolve Hutton's dilemma for students of structural geology today. To understand how this is accomplished, let's look at how the conservation laws might be applied. Let's, for example, consider 1D conservation of momentum. We're looking here at the Lake Edison granodiorite from the Sierra Nevada, California. Note the length scale, 10 centimeters. And let's designate this time T1. The granodiorite is cut by a younger dike. Both of those features are cut by a still younger joint, an opening fracture, but it's about to slip and turn into a fault. Again, think of this as time t1 and focus your attention right here on this little white box. Are you ready for a small earthquake? There it is. At time t2, the dike has moved to the left and into the fixed white box. Perhaps you need to see this again. There we are at t1. Here we are at t2. The question is, how does the momentum of rock in that box change from t1 to t2? Well, Newton proposed that the rate of momentum change is equal to the force. That is, the rate of change of mass times velocity is equal to the mass times the acceleration, and that is the force. Here we're going to think about this in terms of surface forces. We'll use the stresses. And we're going to think about it in terms of gravitational forces. We'll use mass times the acceleration of gravity. And I've put some arrows on this little box. You can see the stress, that is the surface force per unit area, acting on the right side of the box, that acting on the left side of the box. And here's the gravitational force per unit volume, acting on the quantity of mass in the box itself. So our word equation says that the rate of momentum change is equal to the resultant force plus the body forces. But something's missing. Momentum is going to be carried in and out of this box during deformation. And we'll look at that in the next slide. To keep track of the rate of momentum flow in and out of the box, we're going to use the velocity times the density times the velocity. So rho times v, that's the momentum. The rate of momentum is the velocity times that quantity, and this is all per unit volume. So now our word equation says that the rate of momentum change in this little box is equal to the resultant surface and body forces plus the rate of momentum in minus the rate of momentum out. And we've represented that graphically here with these rates of momentum coming in and out of the box. So if the rate of momentum in exceeds the rate of momentum out, the rate of momentum must increase in the box. If the rate of momentum in is less than the rate of momentum out, the rate of momentum must decrease. In other words, momentum is not created, it's not destroyed, it is conserved. We are conserving linear momentum in one dimension. Now, of course, this must occur everywhere in the Lake Edison granodiorite as faulting proceeds, and it must occur in 3 dimensions. What Cauchy did was to use calculus to write this word equation symbolically to derive his first law of motion. So let's look at Cauchy's laws written out using the symbols of calculus instead of this word equation. Well, this may look a little daunting, but here are his first 3 laws, and we can see in this the vestiges of Newton's mechanics. Here's the mass density times the change in velocity with respect to time. Well, that's an acceleration. So we have mass times acceleration on the left-hand side. And on the right-hand side, we have the surface forces per unit area and the gravitational forces. So in essence, we have ma equals F, but now we have it in a form where we can understand the development of geologic structures. The second law is vastly simpler. It boils down to just the shear stresses, the conjugate shear stresses being equal. So Hutton's dilemma is resolved, and this is material that, by my own experience, can be understood and appreciated by undergraduate students who have recently had their calculus course and their basic physics course. We know that surface forces, according to Cauchy's laws, and body forces cause the deformation. Linear and angular momentum are conserved. I didn't talk about it, but mass is conserved. So Newton's laws are obeyed. And now recalling Playfair's words at Siccar Point in 1788, the immeasurable force which burst asunder the solid pavement of the globe can be quantified. Well, today we have ample demonstrations of how tectonic forces can be quantified using Cauchy's laws over the range of length and time scales relevant to the formation of geologic structures. However, many first courses don't even mention these laws exist, much less showcase their success. So let's look at a few examples of these successes at different length and time scales. Here's a wonderful set of images. When I first saw this a number of years ago, I just about fell out of my chair. What we're looking at here are color contour maps of displacement. Check out the length scale. This is 4 nanometers. On the left-hand side, we have the two components of displacement, ux and uy. Here's our x and y coordinate. And these are SEM images. On the right-hand side, this is the continuum theory, calculations based on Cauchy's laws. And if you make a comparison between, for example, this frame on the right and this frame on the left, it turns out that agreement is good to a fraction of a nanometer. This is essentially a verification of Cauchy's laws at the near atomic scale. And I'm sure I don't need to remind you that these images, which are the displacement field around an edge dislocation in silica, is one of the primary defects in the crystal lattice and is responsible for the deformation that we observe, whether it's ductile deformation in a single mineral grain or deformation at a much larger scale. So this is basically a verification at this scale. Let's jump up many orders of magnitude and look at these wonderful images. So these plots show color contours of displacement, but now at Earth's surface. And this was during the Hector Mine earthquake a number of years ago. Notice the length scale across this map, almost 100 kilometers from one side to the other. Faulting, as you know, is one of the primary mechanisms of brittle deformation in Earth's crust. The displacement in this case is in the look direction of the satellite, and the magnitude of displacement is 10 centimeters as you go through one of these variations in the colors. The left image is the INSAR satellite data. The right image is a fault model, again based on Cauchy's laws. The agreement of observations here and the continuum mechanics on the right is good to a fraction of a kilometer. Here we have verification of Cauchy's laws at the 100-kilometer scale. Well, I could go on with many other similar examples, but let's take a look at a different problem. I've referred to this as Cauchy's dilemma, although I expect he never thought of it this way. His first laws are shown again here. Here are the second law. And if you look at these, you can see 6 equations, 1, 2, 3 for conservation of mass and linear momentum, 3 more for angular momentum. So 6 equations, but how many dependent variables do we have? We have 3 velocity components, Vx, Vy, and Vz, and there are actually 6 stress components that are independent. A total of 9 unknown dependent variables. We have more variables than we have equations. The equations cannot be solved. So what am I talking about when I'm suggesting that we should be teaching Cauchy's laws to our undergraduate students? Well, of course, there's a solution to this, which people have known for many, many years. And it depends on the properties of the rock itself. So let's just look at that briefly. I'll focus on the 2 simplest constitutive laws, which are going to resolve Cauchy's dilemma. Hooke's law for linear elastic solids simply says in this example that the stress is proportional to the displacement gradient. The proportionality constant is something we refer to as the shear modulus. Using a set of equations like this, we can come up with the underpinnings of solid mechanics and understand, as I'll show you in just a bit, much of the deformation we see exposed in outcrop. Another possibility is to take Newton's law for a linear viscous fluid. Here, the shear stress is proportional to the change in velocity with respect to position. This is essentially the rate of deformation. And this is the underpinning for the vast field of fluid mechanics. So both solid and fluid mechanics come out of Cauchy's laws by choosing an appropriate constitutive law. Well, let's look at a few examples of how this might be applied for the structural geology student of today who might have found themselves at an outcrop like this. Here we are at a wonderful place, Crackington Haven in Cornwall, and the outcrops there are literally littered with small veins, opening mode fractures that have amazing geometries. There are actually 3 sets of veins in this outcrop. And if you look at the detailed geometry and structure of these veins, build models based on linear elastic fracture mechanics, much of what you see in this outcrop and many of the others there can be explained. Taking up the other constitutive law that was suggested, Newton's law for the linear viscous fluid, many of the things that we see in this sort of remarkable demonstration of fluid behavior of rock, lava erupting from fissure eruptions on Kilauea volcano, can be explained. And even something like this, a little more complicated, but what we're looking at here is, again, the Lake Edison granodiorite. Here's an older dike. The other part of it is here. This is a small left lateral fault segment. The other segment is here. So between these 2 faults, at a scale of a few tens of centimeters, there's a step. That's a step to the right, and these are left lateral faults. So this is a zone where the compression increases, and this drove the deformation out of the elastic field into plastic field. And this dike, which was perhaps 10 centimeters thick, got stretched, got thinned, and a myelinitic fabric develops locally around that compressional step. So this is an example with a little more complex constitutive law that, used with Cauchy's laws of motion, allows us to understand these amazing structures. So let me just conclude with some points I've been trying to make. Hutton's principle of uniformitarianism and Cauchy's laws of motion provide universal and foundational concepts for a new curriculum in structural geology for undergraduate students. Teaching with this curriculum builds on the prerequisite courses for the undergraduate major, particularly physical geology, calculus, and physics. Teaching with this curriculum makes it clear how Cauchy's laws of motion resolve Hutton's dilemma of being unable to quantify the deformation associated with geologic structures using Newton's mechanics for isolated point masses. And it also makes it clear how the Constitutive Laws resolve Cauchy's dilemma of having too many dependent variables, and it enables one to solve his equations for the motion of brittle, ductile, and viscous deformation at all the relevant length and time scales that structural geologists might be interested in. Well, let me finish with a few acknowledgements, particularly my mentors who introduced me to structural geology: Donald McIntyre at Pomona College, Arvid Johnson at Stanford University, and John Ramsey and Neville Price, who taught that wonderful MSc course at Imperial. I want to also mention the students who were there with me that amazing year, many of whom are still active structural geologists and who played a role in all of us learning more about the exciting field of structural geology. I want to thank Stanford University for providing an amazing place to learn and teach. I want to particularly thank my PhD students who are my partners in research. I think each of them deserves a small piece of the palladium in the medal that I have received. And I want to thank Steve Martell, my co-author par excellence, who worked with me on our new textbook that introduces this new curriculum. And I want to thank the editors at Cambridge University Press for this book, Structural Geology, A Quantitative Introduction, for having the courage to publish a textbook which is quite unlike any of its predecessors. And finally, James Hutton and Augustine Louis Cauchy, who sought truth through critical observation and logical rigor. Thank you very much.
Absolutely, Nicky. Thank you very much, David. I'm not sure that, seeing those photographs, I also did the masters in Imperial, or at least the course, whilst there as a PhD student, and visited those places with Neville, and so no doubt you've enjoyed the cream teas of Devon and Cornwall as well.
Absolutely.
I think we're going to close on that. That was really interesting, and certainly a thorough change in the work of what structural geology has become. I mean, many things changed with the invention of seismic. You know, John Ramsey was very much of the ilk you're describing, and then everything got very big with the availability of seismic data as we saw the subsurface in a completely new way. And I mean, it was Bert Bally who took me from being a sort of what I would call a normal structural geologist in those days to someone who looked at things completely differently through the eyes of stratigraphy in many ways. I think in that process we probably lost things on the mechanics, undoubtedly. Great. Well, thank you.
Thank you.
I think